Hello students. So let us look into the next topic, that is called as the minimum description length principle. So we have already seen about or discussed about the Occam's razor, right? So in the decision tree, on what basis you are going to select which decision tree is better. So we used this particular principle called as Occam's razor, which is a very popular inductive bias now that can be summarized as choose the shortest explanation for the observed data, or we can say that choose the shortest from root node to the leaf node which is having the shortest distance or the smallest decision tree. So you are going to select that one, so which we call it as Occam's razor, because this is one of the inductive bias. As you know that any learning algorithm, every learning algorithm has got some inductive bias, right? Some assumptions we are going to make. So now we are going to see that how we can use the concept of Occam's razor. That means how we can put an inductive bias into our Bayesian perspective. That means in our previous section, so we have seen the maximum a posterior hypothesis, right? We have seen what you mean by maximum a posterior hypothesis, and from that we derived or we came to the maximum likelihood hypothesis, and we tried to establish the relation between the sum of squared errors, etc. Now let us consider a Bayesian perspective on this particular concept and a closely related principle now which is called as minimum description length principle we are going to see, right? So just like how we had Occam's razor, so or when we are talking about decision tree, now we were telling that always try to select the tree which is very small, right, based on this particular principle. Now when you apply or when we consider a Bayesian perspective of this particular concept, now can we obtain similar to that, that is which is called as minimum description length principle. So as the name says that minimum description length, that is whichever hypothesis which is having minimum description, now we try to select that hypothesis first, right? So now let us consider the minimum description length principle. So this particular principle, now it is motivated by interpreting the definition of H map. So we are going to bring the concept again of maximum a posterior hypothesis, that is H map, in the light of the, or we try to bring that particular concept and also look into the concept from the information theory. So from some of the concept from the information theory and MAP, now we try to get a relation and we say that minimum description length, that means whichever hypothesis is having minimum description, that one is the best one, or we can say that will be your MAP. So now consider again the definition of H map. So what was the definition? Already we have seen this particular definition. Let me take the cursor. So we have seen this definition. H map is equal to what? Argmax of probability of D given the hypothesis H into P of H. Now this can be now expressed, so we can try to express this by applying log to this, right? So now we will apply log to this particular term. So then we get H map is equal to argmax of all the hypotheses belong to set of all hypotheses. Now we are going to apply log to this term. So we know that log of A into B is log A plus log B. So we use that for particular thing. So we apply log of first term probability of D given H plus log of probability of H, right? So now this, when you look here, now this particular equation after applying log, now we have got argmax. Now argmax means what? You are going to maximize, right? Now which is similar to minimizing the negative quantity. So that means minimizing the negative quantity is nothing but maximizing the positive quantity. So already we have seen, like say for example, now you have got -3, right? So now you want to minimize this, you want to bring this. So if you are going to minimize this, what you are going to do? So after this, now you try to get -2, right? So then you get -1. So then then 0, like this you are minimizing. Now you see that when you are minimizing the negative quantity, actually what you are doing, you are increasing. If you add right? If you increase the positive quantity in this particular term, if you increase the positiveness on this particular term, actually you are decreasing. So when you have got here H map is equal to argmax, which is nothing but so you have a positive quantity. Now equivalently or alternately we can write it as H map is equal to argmin. Minimize the negative quantity in this. So what is that negative quantity? So that means we are going to say minus log of P of D given H minus log of P of H. So alternatively we are going to write. See why we are converting this, why we are going from max to min, because we want minimum description. So we want to establish a relation, that is a minimum description. So we bring this argmax into argmin. So which is nothing but minimizing the negative quantity is nothing but maximizing your positive quantity. So we have argmax. So now we convert it into min by considering the negative term, right? So now it can be interpreted, now this particular statement whatever we got here in the previous step, now it can be interpreted as a statement that short hypotheses are preferred. So what it says, because we are minimizing, so you are minimizing the arguments, right, whichever you are having, that is minimizing the term. So minus of log of P of D by H minus log of probability of H. So you are actually minimizing. So we can say that now we are considering the short hypothesis are preferred. Now consider a problem. Now let us look at information theory. Now in our information theory, now if you try to consider a problem of designing a code, so we want to design a code to transmit messages drawn at randomly. Now you want to transmit some messages through the through our internet or certain medium, right? So you have a message, or say for example telegram. So initially we were having the particular concept of the telegram. Now when you want to transmit a message which is drawn at random, so now we cannot transmit the message completely because the messages will be very huge. So what we want a coding scheme. So we have some schemes in information theory called as Morse code. So we have some of the coding theory now through which we encode the message. You have one particular message, we try to encode that message so that it becomes very small, so it is easy for us to transmit that particular code, and at the receiver end that particular code is decoded back into message. This is how the concept was there, or it's there in information theory. So now when you consider a designing of such a particular problem where a code to transmit message drawn at random, where the probability of encountering the message I. So what is the probability that you are going to get I message? Randomly you are going to select any message I is P of I. Now we are interested here in most compact code. That means now we want to design a code which is very, very small, right? So minimum. So we want a very compactable code, so that already message is huge. We are converting that, you are encoding that message into some code form. You are giving some code to that, and you want to transmit that particular code, right? So when you are going to do this, now what we have to ensure, we want to have a coding scheme which is very compact. So to minimize the expected code length, that what code you are going to give, that also length should be very small, which should be very compact. So to minimize the expected code length, now we should assign a shorter code to message that are more probable. This is what they identified, researcher, because it is very common. Say for example, now if you take one particular paragraph of English statement, now in that paragraph, how many vowels you are going to get? Because whenever we read a paragraph, we know that maximum number of characters are vowels, or let us say that some words will be there which are commonly or frequently occurring in one particular paragraph. So like and, is, there. So if you have some words which are going to occur more number of times, now for those particular words, now we can give a coding scheme whose length is very small, because these words are coming more number of times. So you give a code for that particular word now whose length is very, very small. So then you can compact your code. That is a common or simple logic what is been applied. So the optimal code. So the optimal code, that is code that minimizes the expected message length, assigns what we are going to say minus this is minus log of probability of I, right? What is P of I? The probability of having that particular message, I message. So we try to assign minus log P I bits to encode this message I. So whatever the message I is there, now we want to encode that particular message. Now we will refer to the number of bits required to encode message I, right? How many bits is required to encode a message? Say for example, now if you have got, like say this particular word minimum, you want to encode it. Now I can, for M, now I can have a scheme wherein which I can encode this M as 10, I with one particular value or one digit, because when we are using this coding scheme, it will be either 0 or 1, then N is coming for N, so I can give some other code for that, right? So now again I, already for I what code we have given, the same code. Like this, now when you convert this entire word into a particular code, the length of this code should be as small as possible. That is our concept. So now we will refer to the number of bits required to encode the message I using code C, right? Code C is what? This capital C is what? The number of bits in this code. So this is your I, let us say this is your I. Now, so this is the code. Now if you say capital C, now in this code 1, 2, 3, 4, 5. So we have got 5 bits in this particular code C. So bits required to encode message I using code C as the description length. So we call it as a description length of message I with respect to C, and this is denoted as LC of I. So what is this LC of I? The notation LC of I is the description length of message I with respect to the code C, with respect to the code C, and it is denoted as LC of I, right? So you have to remember this. So this we are trying to bring the concept from our information theory. So now if you take your HAP, that is the maximum a posterior hypothesis, what was that hypothesis? We have alternatively changed HMAP is equal to arg min of minus log 2 to P probability of D given H minus log of probability of H. Now let us interpret this equation according to the information theory or the coding theory. Now here this term, second term, log of P of H, probability of all the hypotheses. So log, that is minus, so this is minus, okay? So minus log of P of H. Now this is the description length of hypothesis H under the optimal encoding for hypothesis space H. So we know that P of H means what? We have got a set of all hypothesis space H, capital H. We have so many hypotheses in that. So you are going to check the probability of the hypothesis. So now when we convert this P of H into our notation with respect to the coding theory or information theory, we can say, so we can write it as L of C of H, right? So this is nothing but what? This is the description length of hypothesis H. Description length of hypothesis H under your coding scheme C, capital C, over the set of all hypothesis H, capital H. Now this is equal to minus log of P of H. So now this entire second term, now we can represent it as L of, for coding scheme H, over the set of all hypothesis capital H is of small h. Now this is equal to what? Minus, this is equal to minus log 2 of probability of H. Now where this C of H is the optimal code, that is the smallest code what we are having, we can represent for our hypothesis space H, right? So first term we have represented like this. Now let us come to the another term. So minus log of P of D given H for the data set. Now we can say that minus log 2 P of D given H is the description length of training data D, right? So now we have got training data. Now description length of the training data D given the hypothesis H under some optimal coding scheme. Now that can be written as, now this can be written as L of the coding scheme, optimal coding scheme C. Now for what? This set of all data set D given H of what? D given D by H. Now this is the representation. This is equal to what? Minus log 2 P of D by H. So now these two terms in our H map, we are converting, or we are trying to represent that with respect to the concept of information theory. So now we overwrite, so we rewrite this equation. Now H map is equal to argmin of what? So what is the first term? So we will say argmin of LC of H plus LC of D given H of D by H. So the same. So we are adding these two, because this entire we are considering minus. We are considering, now see here, LC of H equal to minus log of P of H, and here also minus log of P of D given H. Since we are going to consider that minus term also, so here we just say LC of H plus LC D given H of D by H. So we will rewrite that particular equation. Of this equation, so is equal to argmin of this term plus this term. So where C of H and C D given H are the optimal encoding scheme. So now these are the optimal encoding scheme. One is for set of all hypothesis. The next one is for the given data, for set of all data given hypothesis H. Right? Now when you consider this particular equation, the minimum description length principle. Now this minimum description length principle, it recommends choosing the hypothesis. You have to select, or it recommends that selecting the hypothesis that minimizes the sum of these two description length. So right, so what is our now the actual way of selecting the minimum description length policy, or minimum description length principle, is that now we have two terms. So we have here two description length now in our equation. Now you are supposed to see that now you are going to minimize this term, and some of these two terms has to be minimized. Now assuming we use the code C1 and C2 to represent the hypothesis and the data given the hypothesis. Now if you are going to represent C1 as your hypothesis, see here, so this term C of H is there, right? Now if you represent C1 for hypothesis, so then this can be written as L of C1. And if you use C2 to represent the data, so that means here D given H, right? C of D given H is there. Now this we can represent it as C2. So then in place of that we are going to assert L of C2. Right? If you use the code C1 and C2 to represent the hypothesis and the data given the hypothesis, now we can state the minimum description length principle. So now we are going to define the minimum description length principle. So like say in the examination, if they may ask you, explain or write a note of minimum description length principle. So you have to write from the beginning. So you are going to talk about Occam's razor, a point on Occam's razor, then MAP, then the points of how we are going to get the concept of information theory, then this from that equation of H map, how we are coming to this particular final equation. Now this is our minimum description length principle. What is that minimum description length principle? Now it is given as HMDL. HMDL is equal to argmin of, for all hypotheses belong to set of hypotheses, LC1 of H plus LC2 of D given H. Right? So this is how we try to understand, or we try to apply the Occam's razor concept into our Bayesian theorem, or into our Bayesian learning. So now the above analysis shows that if we choose C1 to be the optimal encoding scheme for hypothesis CH, and if we choose C2 as the optimal encoding scheme for C of D given H, so then we can see that H of MDL, that is minimum description length policy, is equal to MAP, that is the maximum a posterior hypothesis. Now whatever the maximum a posterior hypothesis we have already defined, we have already understood, it is nothing but it is minimum description length principle only. So what the Occam-Razor was telling when we discussed the decision tree, you select a tree which is very small. So now the same thing here also. Now we are, when you apply the Bayesian theorem and when you get a maximum a posterior hypothesis, actually what is happening is that you will see that minimum description, that means hypothesis which has got very minimum description only is been selected. So thus the minimum description length principle, now it provides a way of trade-off hypothesis complexity for number of errors committed by the hypothesis. That means now there is a trade-off between your minimum description length hypothesis and the other hypothesis where you are going to get the error. That means if we cannot say that this MDL or the minimum description length hypothesis or the principle, if you are going to apply, you are going to get the best hypothesis which reduces the error. We cannot tell guaranteely, right? We might be having, so we might be having many other very complex hypotheses. See, you want to have a very simple hypothesis, minimum description means what? Very simple hypothesis. Now there are certain examples wherein which now you have more complex hypothesis which reduces the error. Instead of selecting that complex hypothesis which is going to give a very less error, you are going to select a simple hypothesis based on this principle MDL, now which might increase the error. So now there is a trade-off. Now it is left to you how you are going to select, whether you want a complex hypothesis and where error is less, or you want a very simple hypothesis where error is little bit more compared to that. So it might, so depending on that, so it might select a shorter hypothesis that makes a few errors over a longer hypothesis that perfectly classifies the training example, right? It might happen sometime that a complex hypothesis may classify the training example correctly, but instead of considering complex hypothesis, if you are going with the MDL, you will be selecting very simple hypothesis, but little bit errors will be there. If you are okay with such a learning system where little error is acceptable, then it is always better for us to look simple hypothesis rather than very complicated hypothesis. Right. So now this is the concept what we have discussed, that is minimum description length concept. So in the next topic, now we will be looking into the Navy Bayes classifier. So already we have seen what is called as the Bayes theorem. Bayes theorem, it's also called as Navy Bayes theorem. Now that particular Bayes theorem or the Navy Bayes theorem or the Bayesian learning, now how we are going to use it for as a classifier. So how you can try to, when a new instance comes, how you are going to classify by using this particular concept. So these things now we will discuss in our next topic. Okay, so now try to understand this minimum description length principle. So but to understand this, you have to understand, go back once again, look into the maximum a posterior hypothesis, so that the things becomes more clear. So let us look into the Navy Bayes classifier in our next session. Thank you very much.